Okay, good afternoon. So we are going through the assignment, all right? And we'll start with the question one of this assignment paper. So question one says a manufacturer of steel ingots as plants of two cities, A and B. The ingots are supplied for markets C, D, E, and F. The manufacturer wants to know the pattern of shipment from each production plant to each market that would minimize the total transportation cost. You are given the following data on capacity and demand and also the unit transportation costs. So we have the plant capacities, that is in units each, from origin 1, plant A, 3,000, origin 2, plant B, 1,000. Then the destination's demand units. Destination 1, market C is 800. Destination 2, market D is 1,200. Destination 3, market E is 300. Destination 4, market F is 1,700. And then these are the unit transportation costs that we have. Okay, so from origin 1 to destination 1 is 5. From origin 1 to destination 2 is 8. Origin 1 to destination 3 is 2. Then we have origin 1 to destination 4 is 6. From origin 2 to destination 1 is 7. Origin 2 to destination 2 is 5. Origin 2 to destination 3 is 10. Origin 2 to destination 4 is 4. All right, so this is on what we call on transportation. Okay, so and then the best method we are going to use here is the round method. Okay, so the solution that supposed to be done is here. So from origin 1, plant A, the destinations, we have from origin, that is origin plant A, destination 1, 5, origin 1, destination 2, as per this information. Okay, origin 1, destination 1, is 5. Origin 1, destination 2 is 8. Origin 1, destination 3 is 2. Origin 1, destination 4 is 6. This is just what we have. So these are the ones. Origin 1, destination 1 is 5, 8, 2, and 6. Okay, from this information here. All right. And then we get to the other one. Origin 2, destination 1 is 7. Origin 2, destination 2 is 5. Just like that. So we have this information here. Okay, so plant B, origin plant B. Okay, origin 2 is plant B. So these are origins that we have. So this is origin 1, origin 2. Okay, and then the demands are these ones. So the demand, we have the designated demand. We need to balance up. So the summation of demand will be equal to the summation of supply in transportation problems. Okay, so the capacities, plant capacities, 3,000, 1,000. So the total here is the summation of supply. Okay, so supply is equal to 4,000. Then summation of demand, or demand summation, is equal to its addition of all these ones, which is also giving us 4,000. All right, so meaning that the table is balanced. Okay, so the rules of transportation problems are that number one, need to balance the table. Okay, so balance the table. The summation of supply should be equal to summation of demand. This is on the aspect of balancing the table. Of course, the table is already balanced. So using the appropriate VALM method, VALM uses penalties. And to get the penalties, select the two smaller numbers in a given row or column and subtract them. Okay, so VALM uses penalties. And to get penalties, select two smaller values. Select the two smaller values in a given row or column. So in a given row or column and subtract them. Okay, so that's what we have. In a given row or column and subtract them. All right, so this is what goes on. So here the penalty, first penalty was 5 minus 2, which is a 3. And the penalty here was 5 minus 4, which was a 1, which is a 1. All right. And then in this other one here, The penalty was 2, which is 7 minus 5 is 2. Here it's a 3. The penalty was 8. The penalty here is actually 2. So we select the highest penalty from all the penalties. The highest penalty from all these penalties is 8. Okay, which is this one. So meaning that the value that we have here, the demands that we have the demand of 800. There is demand of 800 here. There is demand of 1,200. Then there is demand of 300. There is demand of 17 here. So from the highest penalty of 8 here, 300 should go in the smaller of these costs, so 300 came here, or 300 came through at this point. Okay. Then meaning that here would have remained with a 2,700 after a 300 entered. So 2,700. Okay, then the other penalty from all the penalties would have had the penalty after this one entered, would have had a penalty now of 3. So a penalty of 3 means that we check on the supply and demand which one would actually meet the demand. Okay, so from here, we know that, okay, the 300 entered here using the penalty of 8. Then the other smaller value on the penalty now, here, this would have gone. First penalties would have cancelled them. Then meaning that the second penalties, the highest penalty would have been a 3. So we now select the 1,200 should go in the smaller of these costs, but it cannot go because here the smaller of the cost is 5. So meaning that what would enter here is a 1,000 coming from this end. So 1,000 comes here. All right, so 1,000 comes here, which is this one. 1,000 comes here, meaning that this would have closed up. This is 300 would have closed up here. Then this one would have also closed up the 1,000 this side. And then we now need just to start reconciling, meaning that if the 1,000 comes here to have a 1,200, a 200 comes here so that it can reconcile. It can give us a 1,200. Okay. And then on this one, the 1,700 will not come here. It will come here so that it can balance up, because the 1,000 already it has closed up here. So we can't put any figure here. So this 1,700 should come here. Okay, and then A 300 already came here, a 200 here, meaning that this 800 should just come on this one. And then the total cost, testing for multi-phase, of course, testing for the generation, the supply, how many supply and demand we have. 1, 2, 3, 4 demands and to supply these ones. So it's m plus n minus 1 is equal to 5. That's the 5 that we have, as we can see on these ones. So 1, 2, 3, 4, 5. Okay, so the testing for optimizing using the stepping stone method. These second numbers are called basic variables, and then empty cells are non-basic variables. So these empty cells, this one is an empty cell, this one is an empty cell, this one is an empty cell. So we are just now sorting out. So we need to find the C bar 21. C bar 21 is this one. So a C bar 21 is this one here. C bar 23 and C bar 24. So this is C bar 24, C bar 23, C bar 21. All right, so these are the C bars. Okay, so the C bar 21, C bar 23, C bar 24. So we can now sort out the issue. So the way we're going to sort out our issue here is that we need to see, for C bar 21 is 7 minus 5 plus 8. So 7 minus 5 plus 8 minus 5, which is giving us positive 5. C bar 23 is 10 minus 2. 10 minus 2 plus 8 minus 5 is giving us 11. C bar 24, 4 minus 6 plus 8 minus 5 is giving us positive 1. So in conclusion is that since all non-basic variables empty cells are greater or equal to 0, the solution is optimal with the C11 800, C12 200. So C11, these are the ones. C13 is 300. C14 is 1,700. And of course, C22 1,000. So the total cost is giving us 21,400, and that is an optimal solution for this one, as backing up question 1 solution. Then getting down to question 2 now. So getting down to question 2. Question 2 reads, the Commonwealth compound has plants at Ndola, Mfulira, and Chingola. Its major distribution centers are located to Kitwe and Chilabombwe. Okay, the capacity of these plants during the next quarter 1,015 and 1,200 machines. The quarterly demand at the two centers are 2,001 full machines. The transportation cost per machine, a kg is 0.08. The difference in kilometer between the plants and the centers is given in the table. Okay, so we have Ndola, Mfulira, Chingola, Kitwe, and Chilabombwe. We have these ones. Okay, so give the minimum transportation cost distribution schedule in the case of the entire supply from all the sources that could pass through any source or distribution before it is redistributed. So we have the supply and demand. Supply plans dollar 1,01512 total is 37, and the demands from Kitwe and Chilabombo, these are also giving us the 37. The problem is balanced. So the course my machine distance times 0.08, right? So we are getting the 0.08. Okay, so this is 0.08. So we have now, after multiplying by 0.08, we are getting the values, which are these ones. Okay, that is from dollar to Kitwe, 240, dollar to Chilabombo, 40, Mfurira to Chilabombo, 200, Mfurira to Kitwe, 160, Chingola to Kitwe is 80, and then Chingola to Chilabombo is 120. The allocation cheapest routes first, dollar 1,000, cheapest route is 40 from there, among all these ones. Okay, they allocate all the 1,000 from there. The Chilabombo demand left is 400. Okay, from there. Okay, and we have Chingola is 1,200. Okay, Chingola is 1,200. And then, of course, the cheapest route is 80 now from there. Chingola to Kitwe is 80. Okay, so meaning you can allocate all the 1,200. In Mfurira, 1,500, cheapest route is 160. Okay, between the 200 and 160 is 160. So you allocate 1,100. Okay, the demand is satisfied. Remaining 400, Chilabombo. Okay, so Chilabombo demand is satisfied. So first final distribution schedule, dollar to Chilabombo is 1,000. Chingola to Kitwe is 1,200. Then Mfurira to Kitwe is 1,100. Then Mfurira to Chilabombo is 400. And the minimum cost of transportation will give us 1,000 times 40 is 40,000. Chingola to Kitwe is giving us 96,000. Mfurira to Kitwe is giving us 176,000. And Mfurira to Chilabombo is at 80,000. So the total cost is giving us 392,000. All right, so question 3 is on network diagram, and then the way it's supposed to be done, this one, we draw the network diagram, and after drawing the network diagram on the network crashing, this is on the networking. Okay, so we need to understand that this networking, we have to know how long it takes for us to finish working on this network. So as we can see, we have this diagram where it says 1 to 2, 1 to 3, 1 to 4, of course. Then we also have 2 to 5, 3 to 5, 3 to 6, 4 to 6, 5 to 7, and 6 to 7. And then the normal costs, the total normal cost, we have this one. And the crash cost means that it's the cost involved in reducing the project time. All right, so and the indirect cost per week is actually 200. That's the indirect cost per week. It's actually 200. So find the optimal crashed project completion time. All right, so there is an aspect first of drawing the network diagram using the information that is here. Okay, so The network diagram is drawn based on the information given. So we have this kind of arrangement. So we have 1 to 2, 1 to 3, 1 to 4, 1, 2 to 5. Okay, so this is how this diagram came about. 1 to 2, 1 to 3, 1 to 4. All right. Then 3 to 5, 2 to 5, 3 to 5. This one. 3 to 6 and 4 to 6. Then of course 5 to 7 and 6 to 7. So this project was taking 18 weeks, and there are two critical routes that are here for this one and this one. So it's 1 to 2 to 5 to 7, which is giving us 18. Then of course we have 1 to 4 to 6 to 7, which is also giving us 18 weeks. So there are two critical routes that we have here. Okay, so from these two critical routes, we now need to find the activity. I will do an activity table for the activity crash limit. Okay, so crash limit is obtained by subtracting the normal time minus the crash time. Okay, so like here it's a 3, the other one is a 2, subtracting these ones. Then here is a 3, here is a 2, here is a 2 as well. So all these ones, these are how you find the crash limits. Then the cost difference, we actually get it by looking at crash cost minus normal cost. So the crash cost minus the normal cost, that's how you find the cost difference. So in this case, we are simply saying for the first one is 850 minus 700, 700 minus 500, 1, 2 minus 600, 1, 250 minus 800, 1000 minus 700, 1, 3 minus 1, 1, 1, 450 minus 1, 2, 500 minus 400, 850 minus 500. This is how we find the cost difference. So the cost difference is obtained that way. All right, and then the normal total cost in this case was obtained by simply adding, so it gave us 6,500 plus 18 days. So the total cost was obtained by simply adding these ones, which is a 6,500. So 6,500. All right, so 6,500, then plus, so the 6,500 here, then plus 18 weeks, multiplying this one by 200, and this actually gave us the 10,100. So 10,100. So you find looking at this, finding the activity to crash with the least cost per week. So we crashed activity 1 and 2 and 4 and 2, 6 by 2 weeks. It gave us 10,050. We multiply this by the cost per week. Okay, so it gave us 10,050. Then again, we crashed activities 1 and 2 from the critical path, 1 and 2 and 1 and 4 by 1 week, will give us the 13,300. Then the crashing activity 1 and 4 and 5 and 7 by 1 week give us the 16,400, because the duration is reducing the project completion time. The essence of crashing is to reduce the project completion time. okay, from the long period of time that you can finish working on a project to a minimum possible time. Okay, so that's what goes on. In again, crashing activities 1 and 4, okay, then 2 to 5. Okay, so we have 1 and 4, 2 to 5, and 1 and 3 by 1 week. It gave us now the total cost is 16,200. So this is how this network was supposed to be crashed to reduce the project completion time. And we are looking at the ones with the least cost per day as we are crashing the network diagram to reduce the project completion time. All right. So this is how this assignment was supposed to be handled. Okay. For the 3 topics that came through, for the first one, the second topic is question 2. The first topic was on transportation. And the question 3 was on actually network crashing, where the indirect cost was also given. All right. So end here for now.